Hello, this is Alberto Espay from the University of Cincinnati, and it is my pleasure to present to you Parkinson's and related syndromes, time to reject the Bragg hypothesis, which I hope will be provocative. My disclosures are shown here, and I trust that none of them have a bearing on the content of this presentation. Let me start with parting as if it were 1999. This is Bob Burke's seminal paper on alpha-synuclein. I'd like to read what he wrote in this paper. I don't claim to know all the details, but it is so interesting a narrative and is so foreign at the same time. It does feel so distant. We have previously shown that synuclein is upregulated in the substantia nigra following developmental lesion of the target striatum. In this model, synuclein is preferentially expressed in normal appearing neurons rather than those which undergo apoptosis. But because it has been proposed that synuclein may mediate apoptosis, to examine this possibility, we have studied a model in which apoptosis is induced in dopamine neurons by intrastriatal injections of this 6-hydroxydopamine. And in this model, what they observed was a complete dissociation between apoptotic morphology and synuclein protein expression. They wrote, "We conclude that synuclein is unlikely to play a direct role in apoptotic death in dopamine neurons and is more likely in the target injury model to play a role in protection or restoration of neurons which survive." It turns out that this happens at about the time that two pivotal events came onto the fore of our history. One was the discovery of the alpha-synuclein gene in the contursi family, and then the other one was the discovery that alpha-synuclein was the key constituent of the Lewy bodies, and these two forces were too powerful to really prevent the narrative from Burke's laboratory to prevail. And in fact, we were then mesmerized by the elegance of Bragg, from an elegance of Burke to an elegance of Bragg. It was important for us to find a story that would have put the evidence of contursi family, the alpha-synuclein gene, and the Lewy pathology. And this is really what has held our field for the last 20 years, almost. So let's examine how we came to what is referred to as the Bragg hypothesis. This is data that comes from 69 patients with pathology-confirmed Parkinson's disease, and about a number of others without Parkinson's. And all of the brains were stained with alpha-synuclein stain, so that to identify the distribution and the overall staining patterns of alpha-synuclein. And as you see, there was a very little staining. When that was the case, that only involved the dorsal motors of the nucleus, or the vagus nucleus. When it was a little bit more, it involved also the locus coeruleus right before it. And then when it involves a little bit more, it happens to take place or involve the nigra. And so essentially what this meant is that there was a little bit of staining, a little bit more, and so forth. And this thing was made to move from one to another. So this cross-sectional data was made highly dynamic from 2 to 3, from 3 to 4, from 4 to 5, 5 to 6. And that then led to the idea that the pathology, in fact, propagates or spreads or replicate. There was an active element here of alpha-synuclein that moving from the lower brainstem upwards was both necessary and sufficient for the appearance of Parkinson's. It just so happened, of course, that since then the evidence hasn't really shown that the pathology is either necessary or sufficient. And in fact, this was a study done not too long after Brack's hypothesis. This was just everyone from a 900 cohort of patients, taking only those who had alpha-synuclein in the brain, and essentially looking at how many of those had any kind of neurodegenerative disorder. And you can see here that under a third had. And damningly, the distribution or load of alpha-synuclein pathology did not permit a dependable postmortem diagnosis of the specific Parkinsonian or cognitive syndrome. Then from John Duda's laboratory, this came out in 2007, which was another study examining the brains of individuals with incidental Lewy body disease, comparing them to Parkinson's disease, and demonstrating that, in fact, while the incidental Lewy body disease, considered preclinical Parkinson's, has somewhat of a lower density in the nigra, in fact, there is a greater evidence of neuronal loss as measured by tyrosine hydroxylase than in Parkinson's disease. Data that, of course, is against the idea that there is a pathogenic role of alpha-synuclein in Parkinson's disease, and also against the assumption that this incidental Lewy body disease, as expressed by the presence of alpha-synuclein in individuals without Parkinson's, would necessarily mean that those individuals were on the way to developing Parkinson's. When data from 3 different studies was combined by Burke, Dower, and von Sattel in their Annals of Neurology 2008 paper, they demonstrated that there was no relationship between the age of death and the Brack stage. In that same analysis, which is perhaps one of the most elegant analyses using the same data from Brack, you can see that there is also no relation between the Honeyjar score and the Brack stage, as you can see here. So if we think of what proportion of nigral neurons with Lewy bodies would be related to the duration of Parkinson's, what that relationship will be, we would expect to have a linear correlation or something along the lines of the longer Parkinson's lasts, the greater the proportion of neurons with Lewy pathology. And in fact, the data doesn't quite show that. If anything, there is a negative correlation between the proportion of Lewy body neurons and the duration of Parkinson's disease. If we think in terms of the relationship between the number of nigral neurons and the number of Lewy bodies in the substantia nigra, we would expect to find a reduction over time in the number of nigral neurons and the number of Lewy pathology. But in fact, the data doesn't show that. It shows a positive correlation between the number of nigral neurons and the total count of Lewy bodies. So this is, again, going back to 1999, where Burke was telling us that alpha-synuclein may, in fact, correlate with what is protective in neurons. So alpha-synuclein aggregation does not appear to be necessary for Parkinsonism or for neurodegeneration to occur. The most naturalistic of all models of alpha-synuclein aggregation is not the one where we overexpress alpha-synuclein directly in the mice, but rather where we have a model whereby there is accumulation of a substrate that damages the neurons and then leads to deformation of alpha-synuclein. And this is the GBA homozygous Gaucher's model that in a time-dependent fashion increases the accumulation of leukocyllus fingusine, and that then leads to the increase proportionally of the alpha-synuclein aggregates as these mice age. It just so happened that there is nothing to report about what relationship that leads to in terms of neuroinflammation or neuronal cell death. One would have to contact Pablo Sardi, for instance, the key author of this paper, to learn that there wasn't nothing to report in this particular relationship. In fact, the accumulation of alpha-synuclein in the hippocampus was not sufficient to induce memory loss. Instead, the behavioral abnormalities require the loss of glucocerebrosidase, but not the alpha-synuclein. So this tells us that alpha-synuclein aggregation is not sufficient for Parkinsonism or neurodegeneration to occur. So I think we need to dissociate ourselves from pathology being equal to pathogenesis, although we often imply in our conversations in this meeting, we're going to be often referring to pathology as if it really means pathogenesis. And in fact, there is no support for a primary pathogenic role of Lewy bodies. It appears to be more a consequence than a cause of the problem. And neither the Lewy body distribution nor the density is associated with nigral cell loss, as we've seen. So let's move over to what is certain and what is uncertain. And we're going to have a bit of a biophysical slant to this. What is certain is that proteins must be in their normal state, normal configuration to function. That the minute they misfold, they can no longer function. What is uncertain, however, is that as the proteins misfold and accumulate in that misfolded state, that somehow they are going to acquire virus-like properties. They replicate, propagate, spread from cell to cell, that they become toxic. Now, the transformation of proteins happens all the time. There is a soluble to insoluble phase transformation, as you see here, either mediated by an external surface, we call it a heterogeneous nucleation process, or by acid, acided nucleation. And essentially what this is telling us is that there is a nucleation barrier that is lowered by the catalysis that is induced by this external particle, usually a nanoparticle, could be a virus, as shown perhaps in this example by these two balls, or by a seed, as it were to be the case in prion disorders. It can also be a spontaneous nucleation, meaning that there isn't any catalytic mechanisms for the soluble to insoluble phase transformation, and instead proteins are inherently unstable, as it happens to be the case in genetic disorders in which the SNCA, for instance, implies an inherent instability of alpha-synuclein, or APP mutation in Alzheimer's implies an inherent instability of that protein as well, and therefore its easy transformation from soluble to insoluble, its polymerization indeed. So phase transitions affect proteins, and in fact, soluble to insoluble transformations are well established, well understood in nature. And of course, amyloids, of which alpha-synuclein into Lewy bodies is a form of, Lewy neurites and Lewy pathology in general are amyloids of alpha-synuclein, happen to represent precisely the crystallized state of these proteins. Therefore, the phase transformation of proteins undergo essentially a structural change from natively folded to a cross-beta conformation, very, very stable. A biophysical change from soluble to insoluble, and a biological change from functional to non-functional. And the example that Karim Esed has provided me with the milk, as you see here, is in the process of undergoing this transformation. The resulting cross-beta conformation of the milk protein is no longer functioning, and it cannot be reversed back into its soluble functional state. And therefore, this is essentially a milk that has lost its function altogether. So replication is a well-defined construct that depends on essentially a mechanism. The main mechanism of replication is provided by the double helix. It is not very much sensitive to extrinsic factor. It is, in fact, nucleation independent, and that differs tremendously from crystallization, which we've seen, of which cross-beta sheet is the best example. That's the conformation into which the soluble to insoluble phase ends. That's the structure that's well established of amyloids, including Lewy pathology. And this is an insoluble mechanism that is highly sensitive to extrinsic factors. It depends on concentration, temperature, pH, and is nucleation dependent, of course, with the exception of patients with mutations in which there is no heterogeneous nucleation, but homogeneous nucleation. But this is a process that is passive as opposed to the active process of replication. One of the most important arguments against the idea that we are losing function, but rather that we are gaining it, is the prime hypothesis. And this is a paper from Stan Prusiner, of course, highly influential for his work in Creutzfeldt-Jakob disease, and a Nobel Prize winner, which makes it very difficult to argue with him. But he pays lip service to the idea that there is a loss of function. He, in fact, says in the last highlighted statement here, although the conversion of a normal functional protein might be expected to contribute to a toxic loss of function phenotype, he pays lip service to it. He says in vivo data do not presently support this hypothesis. He argues that knockout mouse models lacking the endogenous cellular form of relevant proteins generally remain free of overt neurological signs, references 147, 149, which do not quite support what he is stating. In fact, those references are showing that those models do have a loss of function mechanism, that there is disease, obviously without the aggregation, because knockout models by design would prevent the aggregation, but would not prevent the behavioral changes and the degeneration, as has been now well established and shown in a variety of different studies, most of them summarized in the reference that I'm showing here in the right lower by Kent et al. So I think it's important to recognize that there is indeed not a spontaneous generation of these accumulates of proteins, but they happen because we're losing the normal soluble precursors. If I show you a map of Indonesia, in terms of the deforestation, you would see that this map is going to look ever so worse in terms of the loss of forest, such that over the years, unfortunately, you can see that there is a loss of forest. We would not speak of this situation as any gain of function mechanism here, whereby the burned, chopped up forest is taking over in spreading from region to region. You could make the case, but really the simpler explanation here is that we're losing forest. So when we think of our way of putting data, and all of you are familiar with the data to information, to knowledge, to insight, to wisdom, we could, of course, go beyond that and get into a conspiracy theory. I think that the data is very obvious that there is always a preceding pathology in most of the patients that go on to develop Parkinson's, but that does not mean that that's the cause of the problem. And so making that story, it can be akin to a fable that perhaps we should reconsider. So in conclusions, I hope that I've conveyed to you the concepts that proteins behaves like proteins, not like viruses. They precipitate rather than viralize or replicate. The alpha-synuclein phase transform into a cross-beta conformation, a state of protein called an amyloid, which is in a configuration that is too stable to be toxic. Alpha-synuclein aggregation is neither necessary nor sufficient for Parkinsonism or brain atrophy to appear. And Parkinson's disease is not a problem of abnormal alpha-synuclein accumulation, but of soluble, normal alpha-synuclein depletion. So a certainty in biology is that once normal proteins misfold, they cannot function normally. Why should we embrace what is uncertain? So this is the reason why the time has come to reject the Bragg hypothesis. The data does not support that elegant hypothesis. It is important because this would allow moving our field from the efforts of aiming at disease modification that are aiming at protein anti-aggregation to soluble protein replacement. This, of course, would not be precision medicine because that requires understanding why those proteins are undergoing the phase transformation, which are the nanoparticles or the nucleating agents that create that transformation. That would be the source of precision medicine. This would be, though, rescue medicine, and it's going to be important and can only happen if we reject the Bragg hypothesis. And with that, I thank you very much for your attention, and I hope that this has been an interesting and provocative session, and I'm delighted to entertain questions.